Right. Welcome back to Quantum Mechanics with Griffiths. Now we were going over section 1.2, also known as the statistical interpretation. So, previously, I introduced this mystery value, psi, and I did not tell you what it actually represented. I just told you that it was the quantum mechanical analog of the classical mechanical values of position, velocity, and acceleration. So, this section is going to be mainly dedicated to trying to interpret what psi actually means. Now, the first thing that I want to bring attention to is the name of psi. The name for this quantity is known as the wave function. And I hope that this immediately draws some red flags in your minds because of the fact that it is called a wave function. So the very fact that it is called this implies that our function, our quantity psi, is somehow related to a wave. Now, waves are not localized in space. They do not have a position. It makes no sense to say that a wave is located at some point in space x, y, and z. Instead, waves spread out throughout space, and what we say is a wave saturates a given area. Now, this is very much contradictory to our quantities from classical mechanics. Position, velocity, and acceleration are localized quantities. A particle has a definite position in classical mechanics. It is either here or it is not here. Same thing with velocity. Either has a velocity or it has some other velocity. Same thing with acceleration. So instantly, this should raise about some concerns because how can we describe something such as position, velocity, and acceleration, which is localized, using something like a wave function, which, according to the definition of a wave, is not localized. And the way that we kind of resolve this issue is using what is known as Born's statistical interpretation of quantum mechanics. And what this basically says is that the magnitude of psi of x comma t squared is equal to the probability of finding a particle at a given position at time t. And what this essentially implies is that there is some sort of indeterminacy that is fundamental to quantum mechanics. Even if we know our quantity of interest, psi, exactly, even if we know our wave function exactly, we cannot actually know the exact position, velocity, and extending this, even things like energy and momentum at any given point. We can only say that there is a very high percentage chance of a particle being in some specific location or having some specific velocity. And this is kind of the first mental hurdle of quantum mechanics that we need to overcome. Because we've spent 2 years learning about classical mechanics, and all of the principles we've learned from classical mechanics seem to point in the exact opposite direction of what quantum mechanics is suggesting. So whereas classical mechanics is localized and focuses on defining definite values, quantum mechanics is apparently all about probabilities. And apparently, in the quantum world, we actually cannot tell any exact parameter of a system, such as position, velocity, acceleration of a particle. This fact is something that Einstein and his various contemporaries back in the day agonized over, and I would encourage you to also agonize over this idea, because this the fact that the wave function psi describes the probability of finding a particle somewhere actually arises some very interesting and somewhat concerning implications. So to kind of to kind of go into what these implications are, I want to ask a question. So suppose that we measure a particle at some. Suppose we measure a particle's location, and let's say that it is x of t equals a at time t. Let's say, now the question I want to ask is, what was the position right before we measured it? And if we were analyzing quantum mechanics through the view of a classical mechanicist, shall we say, we would answer with what is known as the realist position, which says that the particle was always at position A. And this is what makes sense to us physically. If I have a ball sitting in the middle of the room at some location on the floor, and I measure the location of the ball, right before I measured it, the ball was still in that exact same location. So this is the position that we are comfortable with. It is what supports the hundreds of thousands of observations we have made as classical mechanics physicists. Now, unfortunately, the realist position is not correct, or at least if it is, we do not have any supporting evidence that it is. Rather, the most commonly accepted answer to this in quantum mechanics is known as the orthodox position. And what the orthodox position says is that the particle actually does not have a defined value of x of t prior to measurement. And this should automatically make you froth at the mouth if you're not familiar with this concept. Because apparently what this is saying is that before we measured the position of our particle, it actually had no position. It was, in fact, everywhere at time. And that by measuring, the very act of measuring somehow gives the particle a position. And this is obviously false according to our experience with the real world. Just because I measured the location of a ball on the floor, that the ball was obviously there before I measured it. It did not just pop into existence at the location where I measured it. And this is kind of, once again, going back to our hurdle, that quantum mechanics has indeterminacy. And in fact, we actually cannot know, we cannot predict the position, momentum, velocity, etc. of our particle. Rather, we need to measure it to actually determine what value it takes. There is no function force equals mass times acceleration that allows us to predict the position of the particle with respect to time. Rather, we can simply analyze where the particle is most likely to be at any given time. Now, this orthodox position can actually be elaborated even further. So, say that we measure, suppose we measure the position a second time right after the first. What is the position measured? So I measured the position of my particle to be at x equals a. So suppose that right after I make my first measurement, I continue and make a second measurement. So the question now is, what am I going to measure on my second measurement? And this time, we actually can apply our knowledge of the real world and classical mechanics to this, obviously the particle is going to be at that exact same position. If I measured a ball that is stationary on the floor, and I do it again 1 second later, the ball isn't going to randomly change its position. However, that kind of brings about a it brings about a bit of a conundrum, because remember that psi determines the probability of our particle being at any given position. So if we say that a particle's wave function originally looked something like this, what does this tell us? Well, this tells us that there is a very high likelihood of the particle being at position A, and there is, in contrast to that, a position like position B would have a very low likelihood of having the particle around that area. So, however, one of the things about probability is that it does not give you perfect results. Rather, your results will vary, and they only follow a pattern in the long run. So, what is preventing us from finding our quantum particle at some other location C, where it's less likely to be found, but still a non-zero possibility? And the resolution to that is that apparently the act of measurement actually collapses our wave function and causes it to take on a sharply peaked point about our first measurement of A. And this should raise a lot of red flags. I would highly encourage you to kind of suffer a little bit and contemplate the significance of this, because assuming that the wave function is a physical thing, assuming that it is a fundamental part of our reality, apparently the very act of measuring actually changes it, and by that logic, the universe somehow is able to know when we make a measurement. And that is one of the things that, as I said earlier, Einstein and his contemporaries kind of agonized over for a long time. That apparently the very act of measurement, the very act of measuring and observations are apparently kind of fundamentally entwined into our fabric of reality, to put it in a slightly fancy way of saying. And this is something that you should definitely spend some time just digesting, because it is by no means something that is intuitive. Everything we learned in classical mechanics kind of points away from what quantum is telling us, and this result should, on first appearance, sound very illogical and downright impossible. Now, unfortunately, because of the fact that Griffiths is an introductory textbook, its main goal is to just get you acquainted with these concepts, and as a result of that, we actually cannot go very deep into the depth and prove why this is the case. As an example, we never proved the Schrödinger equation. I kind of gave it to you, and we will not for the length of this textbook. We never will. And as a result of that, a lot of the, and this is true for a lot of other things that we'll run into in the over the course of this book. And in many ways, it can be pretty unsatisfying when we introduce a concept and not kind of elaborate and just say, hey, you have to accept this. But this is unfortunately a necessary evil in order to cover just the massive scope of the textbook that is Griffiths. So I will leave you with that, and allow you some time to digest this sort of very counterintuitive process of quantum mechanics.